Okay. Good. Okay, let's see. Good day, everyone, and welcome to this master's class of dimension and complexity reduction, it's called. So you're first year students at the Complex Systems Master. And this is a lecture about trying to approximate the complexity of dynamical systems. So we are going to talk about dynamical systems once again. Something you're familiar with starting with the second year. But first of all, so you're what, 12 students, right? How many students are you in this class?
Maybe 8 or 10.
8 to 10 students, fine. And what exactly is the background of everyone? Because this is important. So are you all with the background in systems and control? Or are you people with different backgrounds? Because I need to know how to calibrate the discussions, so to speak.
I think most of us have a background in systems and control, but I'm not sure if everyone does.
I'm not sure either. Never mind. So the idea is we are going to talk about, maybe for some of you, this is going to be the first part of this class. So quite a number of weeks. This is going to be a recap of things you are familiar with from the second year, because we need to talk about dynamical systems once again. Okay. And we are going to talk about approximating these dynamical systems with other dynamical systems, but of smaller dimension. A dynamical system is a set of differential equations, okay? Like in mathematics, differential equations. Now, the problem is that nowadays, these differential equations, the number of these differential equations and also the number of unknowns can be really high. And when I'm talking high, I mean hundreds, thousands, tens of thousands, millions, and even billions of equations. And this is not a joke. This is true, especially in things that come from discretizing partial differential equations. Phenomena described by partial differential equations, such as the heat equation, or which is the simplest, or such as fluid, the equations that govern the fluid flow, as well as weather conditions. These are PDEs. That means they depend on space and they depend on time. And they need to be discretized so we can compute them on computers, okay? When you discretize such an discretize the space for such a partial differential equation, it means that you get a set of ordinary differential equations which are really, really high. Okay, like I said, they can be billions of equations. How to simulate, how to study, how to analyze billions of equations, systems of billions of equations. It's hard to assess even the stability. Okay, you can't understand what stability is in this case. Okay, and we do remember, all of us, that stability is the main issue in systems in control theory. We like to have stable systems. That's why we do control. Yes, the reason for control is stabilization, so rendering a closed loop system stable. Okay, so the idea essentially here, if there's people who do not really understand what I'm talking about right now, we are going to talk about this thing. You have this this guy, essentially, which we can call sigma, that gets information at the input under the form, for instance, of a signal U. We call this input signal, okay? Input signal. And you can get an output signal. This is an output signal, Y. And the idea is that Y is sigma applied to U. Now the question is, what is this sigma? What is this sigma? People who have studied systems and control theory already know that this sigma can be a transfer function, okay, in the complex domain, okay, so H is a complex function, okay, or this guy can be a set of 4 matrices A, B, C, D. Yeah, this is in the time domain. This is in the time domain, okay, a set of 4 matrices. These are called state space realizations, okay? That's how they are called. But we are going to recall in the first few chapters all of this, because there's a lot of people who are not familiar, or maybe there's a few people actually who are not familiar with these notions, which means we need to bring them back or to show them to everybody, okay? Essentially, so I can make a short introduction to the people who are not familiar with this stuff. So us people in systems and control theory, we need mathematical models. This is a lecture about mathematical models and how we can approximate complicated mathematical or complex mathematical models with simple mathematical models. This is the idea of this class. Simple mathematical models, easy to manipulate, okay, for analysis, for simulation, and for control. Even if we have MATLAB, for instance, and I'm going to ask people here just to make things clear. Are you people familiar with MATLAB?
Yes,
Yes.
I am.
You are,
Yes.
you are, and the others?
Yes.
Yes.
Okay, fine. So everybody is familiar with MATLAB, and I'm happy to hear about it because you're going to have your assignments in MATLAB, and the work, the applications, the exercises are going to be in MATLAB. Even MATLAB cannot compute complicated stuff due to numerical issues, due to computational effort, okay? Because to be able to simulate and to integrate thousands or millions or hundreds of, thousands or millions of equations, it's a difficult task. It's next to impossible. You cannot accurately integrate billions of equations. Or you do it like the people in weather forecast do. You run simulations for weeks, okay, for weeks. That's why they constantly run simulations, because they have to simulate billions of equations, okay? They have to simulate billions of equations, and that's too bad. So the idea is we get this ABCD from somewhere, and ABCD means actually it's a set of equations. X dot is AX plus BU, where X dot signifies dx to dt. So these are time functions. They are the states. They're called the states of the system. So you get this equation, okay, with a dimension of x, usually n. X is a vector in Rn. N is huge nowadays. Yes, because these days the models are getting more and more complicated. Well, think about traffic models. Think about power systems models, where you have all these renewable energies, where you have all these new consumers, such as electrical vehicles, okay? So the models are more and more interconnected and more complicated. Even if a subsystem, a small system, is small, you have thousands of subsystems, and that makes it complicated, okay? So N is usually huge. Is usually huge. If N is huge, it's hard to understand this equation. It's hard to do something about it, okay? If you have a simple equation, say this one, y double dot, y double dot means d2y to dt2, so twice derivative of y, plus, say, what? 3y dot plus y equals u. All of these are time functions. This is a differential equation of a second order system. Yes, okay. So how do you bring this to this guy? Because this is an equation and this is of second degree, okay, of second order, and you have here only equations of first order. This is very easy to do because you call x1 y, then you get x1 dot is x2 is y dot, okay, and then you get x2 dot comes from this equation. It's minus x1, which is y, this is x1, and this is x2, minus 3x2 plus u, and you get a system of equations, okay? x1 dot is x2. And then you can easily rewrite this guy as this one, x1 dot, x2 dot. This is a question of modeling, yeah? This is a matrix multiplied by x1 and x2 plus another matrix multiplied by u. Essentially, the first matrix is 0, 1, minus 3, minus 3, yeah, no, sorry, minus 1, minus 3, minus 1, minus 3, and this is 0, 1. So you get A, this is x dot, this is A, this is x, this is B, and this guy is U, okay? So you get this guy. However, this equation, this is a simple equation. This is a simple example, but things can be really, really complicated, and we are going to give a few examples of that, okay, to set things straight and to get a grip of what's going on here. But essentially, these are the systems that we study. We get this differential equation. This is the dynamics of the system, and then you get measured outputs, which are of this type. This is a matrix C multiplied by the state vector X. X is the state, U is the input, Y is the output. Okay? The idea is that this, and I said X is in Rn, N is very, very large, and we want to find another guy, which is X hat dot, is A hat, X hat, plus B hat, but U is the same because we subject this whole new guy to the same input, and you get the new output because this is changing too, which is C dot X hat dot. You want to find this guy with X hat in R new with what condition? And much smaller, new with new much smaller than n. And you have to ask who is A hat, B hat, C hat. How do you compute these guys? And then you have to ask, how accurate is this? How accurate is this? Okay. So this is essentially, in a nutshell, the problem of model reduction. Model reduction means that you have a mathematical model, or nowadays you have huge amounts of data, okay, because you know that everything now happens in this framework of big data. I'm sure you've heard about it. So if you get a mathematical model, this is a picture from my PhD thesis. It has been designed by a colleague of mine from Cluj. He made it. We were both in the Netherlands at that time. He made it for me, and it's very, very, very nice, and it's a big suggestion. It's a strong suggestion of what's going on in model reduction. So essentially, when you do modeling in the first place, you get huge amounts of data, and you get some hazy guy, which is this one here. This is hazy. You don't know much about this. You know, it's some type of system, probably. You have a few information about it. You've got some modeling ideas, or maybe you perform system identification. Some of you probably have already had a course in systems identification in the 4th year. And do remember that you can get large scale or huge models about the system you're trying to study. And then what you want to do is you want to approximate this guy by something. You want to get to this small guy here, which is clear and easy to manipulate. It's easy to understand, easy to simulate, and easy to be subject to control design. So it's easy to design a controller for this guy because this guy is simple. But the question is this guy relevant for the big hazy stuff here? Is it relevant for the collected data? You fetch this model somehow, but you need to compare it to the reality. You need to compare it because it might be relevant or not. Okay, it might be relevant or not. So that's the big issue. How is this guy relevant for your system? And model reduction usually needs to have a purpose. You cannot just make an approximation and that's it. You need to approximate things. So approximation and model reduction, they are similar notions in this case. And you wonder, how is this relevant? So model reduction needs to have a purpose. I do model reduction for control. I do model reduction for simulation. I do model reduction to preserve certain properties. So you have to capture the essence according to the problem that you need to solve. That's the idea of model reduction and of approximation. You'd like to capture the essence. So this guy here needs to be the essence of the big hazy guy you started with in the beginning. Okay? It has to be the essence of this guy. Okay? So that's pretty much what we are going to discuss. This model reduction stuff is not very new. I mean, it's not very new. It started first of approximating large-scale algebraic system, linear systems. How to approximate linear systems which are very relevant in numerous applications. Okay, and linear systems are everywhere. So that's where it started with approximations of linear systems. Okay. And then later it got extended to the dynamical systems case, and it became quite relevant to this. Okay. So we're going to have in this lecture some lecture slides, and we're going to have a supporting book, which is this book, Approximation of Large-Scale Dynamical Systems by Thanos Antoulas from Rice University in Texas. He wrote this book, which has become some sort of a Bible for this model reduction, collecting quite a number of results, of very important results in this field, and making this very nice book. I made this book available to you on the Moodle of this class, which I'm going to ask you to follow quite closely and stick to this Moodle. So I'm going to show you a little bit about the Moodle of the class. This is the Moodle of the class. It's got a lot of material from last year, which I'm going to rearrange quite soon, and you keep following these things. So you've got lectures, you've got books here, as you can see. We open the books folder, and we can find here a couple of books which I downloaded for you. This is the first book, the Antoulas book, which is very important, and you can always keep in touch with this book if you need to study this subject. Okay, and you've got another book which shows you how these techniques have been applied in industry. Okay, so you've got a couple of books. You also have here more stuff. You've got simulation models. Here is the three simulations, the three examples we are going to study throughout this course. You've got a building model of dimension 50, or something close to 50, 48 probably. You have the CD player system, which is dimension 120. And you've got the card pendulum model, which is a small model of dimension 6, but it's a relevant example. Okay, it's a relevant case study. Okay, theoretical example. Okay, and the simulations and the assignments you are going to do, they are all related to these three systems. Okay, they are in the mat format. So the data is collected in about the systems, about each of these systems is collected in a MAT file. Okay, it's collected in a MAT file. You're going to have to use in MATLAB later on. Okay, for your assignments. Then you've got a couple of exercises here. You've got my PhD thesis, if it's of any interest, because it's based on this subject. It's totally about this subject actually. But it's in the nonlinear setting. So if someone needs to read this to understand some nonlinear stuff and is interested about it, and also has an introductory chapter about the linear systems techniques, they can always consult it. There is no problem about it. And then finally, you've got a folder with the papers to study for exam. So here you've got 14 papers. And each of you is going to pick a paper, it's going to study it, and is going to present it at the final examination for this class. Okay? And this brings me to the administration issues of this class. Okay? Which are presented, I think. They are presented. How am I going to get out of here? It's a bit weird. Okay. Oh, it's here. Okay. Right. Let me go back to the Teams. I want to get out of this Moodle stuff, and I cannot do it. Because I don't want to use the Moodle now. No, I don't want to open it in a browser. I just want to go back to my Teams. What the hell happened here? This stupid app always make it more stupid. Okay. Oh yeah. Just hold on for a sec. Can you see my screen now?
No.
No. Why not? Let me try again. It's not working, but why isn't it working? No. Okay, now it should be. Okay, fine. Okay. Where were we? Oh yeah. And here we've got an administration file and about administration and grading, which is quite short. Okay. So I'm the guy who's giving the lectures. This is my email address. And we do everything on Moodle, where you get labs and you get assignments and quizzes, which are 50% of the final grade. The rest of the 50% being the article exam. Okay. So you get a research article, you get to pick from the folder I just showed you. You need to study and to simulate it. You must make a presentation or a report. It need not be necessarily a presentation. It can be also a report about the paper, where you show me what you have understood. You show me your vision, your view of things, okay? How you view the things, and they show me that you understand the main results. And also you can tell me how it can be improved if you have any idea about it, okay? And finally, you need to implement the examples of the paper, if any. And this is going to make 50% of your final grade. Is it clear?
Yes, it's clear.
Okay.
Yes.
Fine. That's all you have to do. Good. Right. So you need to follow the Moodle closely to see when you get quizzes and assignments. Okay. Good. So you have the book I just told you about. You've got exercises you can solve using pen and paper or MATLAB or Maple, if any of you are familiar with Maple. Maple is a symbolic computation medium. Okay. Okay, yeah, the grading I just told you about, it's about the grading here. This is not relevant because I told you what grading is. I'm going to give you, you need to make the report about the paper. Okay. So this is the aim of this class, is to be a light course on model order reduction. This is something you haven't probably seen before. You must have heard about it before. Again, it's very important because mathematical models are getting more and more complex. This is not something new. Model reduction has come up somewhere in the 60s. And it stemmed from systems identification. It was based on systems identification, and then it was extended to dynamical systems and became a research field in itself. And it's gone extended towards infinite dimensional systems such as PDEs, towards time delay systems, towards nonlinear systems as well. I have been working quite a lot in nonlinear model reduction, if you ask me. So I'm going to present this to you in this class. Okay. Okay. So essentially, we are dealing with mathematical models, right? The question is, what is a mathematical model, or how do you come up with a mathematical model? Okay. You need to write equations that show dependencies between variables of a system. Okay. If you have, so for instance, if you have this guy, it's called the gravitational pendulum. Okay. This is called the gravitational pendulum. This is a body of mass m attached to a rod hanging from a ceiling. Okay. This is the angular position, theta, and it's governed by the gravitational force, G, which is mg. Okay. Now, how do you describe this as a system? How do you describe this as a system? Of course, to get a mathematical model, you're going to use motion laws, okay, or conservation laws, physical laws, okay, from Newton, for instance. So here you've got rotation movement. You've got rotation movement. So what you do, essentially, you're going to decouple. We're going to decouple the gravitational force on two directions. The tangential direction, which is tangential to the trajectory, and the normal direction, okay? The normal direction, which is along the direction of the pendulum, where the pendulum is pointing, okay? And once you do that, you apply the laws of physics, okay? And you add up all the torques, because this is rotational movement, you don't have forces here, but you have torques. And the torques should all of them be in the equilibrium. We assume that there is no external influence, so there is no external torque applied to this guy. Okay? So you have the torque given by the gravitational force, okay, plus the friction torque, plus whatever is external, they're all zero. Then you start writing each of the terms. Okay? And you end up here for the gravitational, you only take at this point the tangential component for the movement of the body, okay? For the movement of the body. So this is going to be something like mgl sine theta, okay? Plus, and here you get the friction torque, which is the friction force times L is the length of the rod, by the way. L, or the beam, is the length of the beam or the rod. Okay, beam or rod. This is how you call this, bara. Yeah? Beam or rod. Okay. And of course, the movement torque, which is m L squared. This is the inertia. Okay. Theta double dot. This is what? This is theta double dot is the angular acceleration. And the friction force is depending on the velocity. So it's something like what? K, which is a friction constant. Theta dot, not double dot, but dot. This is the velocity times L, okay? So theta is angular position. Theta dot is angular velocity. And the theta double dot is angular acceleration. Okay, and this is all equal to 0. And this is the equation governing the pendulum. Okay, now this is a nonlinear equation because of this sign, but if you take the small variations, we know from the 9th grade that sine theta is what? If you take very small variations. What is sine theta?
Theta?
Is theta itself, exactly. Is theta itself. So you get a linear model. So this is the linear mathematical model of the pendulum. ML squared theta double dot M plus MGL theta plus K L theta dot equals 0. And this is the mathematical model, or this is the mathematical equation of the pendulum. Now, if you want to get a first order with A, B, C, D, a first order model, you don't want to have you don't want to have second order differential equations, you take x1 equals theta, then x1 dot is theta dot is x2. You make these notations, okay? x2, and then you get the following model: x1 equals x2, x2 dot equals minus mgl x1 minus kl x2, with the initial conditions x1 0 and x2 0. And this is the mathematical model. Now, how accurate is it and how good is it? That's the question. That's the question you need to ask yourself. You need to wonder about a mathematical model. So you get the mathematical model from data-driven modeling, such as system identification, from what we have just done now. Modeling physical equations, that's what we have just done. We did point B. We have done point B now. Of course, also through interconnecting subsystems, because, for instance, you have more pendulums or pendula. Okay. Huh? Are you guys all right? Okay. So you can get more of these things. Okay. You can get more of these things. Okay. You have a lot of models you can compute like that. But if you interconnect this, so you have here, this is theta I, okay, and you interconnect these things, here you can have an interconnection term. Interconnection. Yeah, and if I is from 1 to n, or 1 to n to capital N, say, yeah. So the resulting model depends, is what is the final dimension of the resulting model? N equals 2 capital N. Because each model I, okay, is governed by two equations. So the final model is going to have dimension 2n, and it can be very, very large. Can be very, very large. Okay. So if you do interconnection, you can get complex or highly dimensional systems. Highly dimensional systems. Now, of course, when you talk about nonlinearities, such as this I just showed you with the pendulum, complexity and dimension are not going hand in hand. So for systems of linear differential equations, indeed, it's the complexity is proportional. The complexity is proportional to the number of equations. But when you talk about nonlinear systems, such as the newly presented pendulum, dimension and complexity are a bit different. They are not exactly the same thing. The idea is that even if you have a limited number of equations or a low number of equations, you can still have a complex model. Okay, in the nonlinear setting. Nonlinear systems are quite tricky about this. Okay, but okay, apart from that, we need, in general, when you write a mathematical model, you need to trade off between complexity and accuracy of the model. Okay, and the fair question now is what is the difference? What is a good model? So a good model is when the difference between the experimental results and the computation results is quite small. If you do compute something using a mathematical model, but this is a fair game, in the sense that it's not good at all, and the experiments show otherwise, then you're back to square one, essentially. So you don't get absolutely anything. Okay. So you do need to have this this trade-off. Okay, you do need this trade-off to be able to make a good mathematical model. Now, again, the question is, okay, the mathematical model that yielded by your technique is good, fine. But what if it's too complex and too difficult to compute or use for anything for that matter? Okay. So what gives? Why do we need model reduction? Because again, I just told you, because we have, even if we have subsystems with simple mathematical models, once you interconnect them, the resulting model is most likely very complex, and you're unable to perform anything on it. Okay. So we have a few examples. Usually very complicated models come from electronics, where you need to implement on a piece of silicon a huge number of circuits, and you have a few examples here. Okay, you have an example here, and in detail, apart from the picture you have just seen, the interconnection, for instance, of the model of this huge electrical circuit is given by this set of equations. I just showed you earlier, where typically the dimension of the state vector, the dimension of X here, which is also the dimension of the matrix A, which is a square matrix, is usually of this range. So millions, billions, trillions, and so on of equations. So this is another example of millions of dimension of millions. The electrical circuits for electronics, okay, for boards, for instance. These are very hard to use. So you need to approximate them. A second example, for instance, is using a gyroscope, which is a device to measure and maintain orientation, and can be used for automobiles. It's used in shipping, aviation, most likely in defense. Okay. So the design of the device must be verified using simulation. But again, once again, I'm stressing this, you cannot simulate if things are too complicated, and you cannot compute anything, or the computational effort is huge. So for instance, this gyroscope can be modeled by partial differential equations. Partial differential equations are pesky. They are troublesome. Of course, there is now quite a lot of theory on the so-called infinite dimensional systems that they generate, and there are quite a number of control techniques, but they are still very, very difficult, because partial differential equations do not benefit from the ease of computing analytical solutions. You know that their Cauchy problems are very hard to compute and usually next to impossible, apart from some very simple cases, such as the heat equation, where you can explicitly write the solution. But in general, you're unable. So usually you need to approximate the PDE with ordinary differential equations, And that's also very difficult, because what you usually do, you know that the PDEs depend on time and space. Space and time. So usually what you do to get rid of the space variable, you discretize the space variables on grids, okay? And you write, in each point of the grid, you write a set or a specific ordinary differential equation. So that means that you have an approximation of the PDE with a set of differential equations which depend on how fine or coarse your grid is. So if your grid is too fine and you have a huge number of points, then this results in a huge number of ordinary differential equations. So it's still complicated. If you have a coarser grid, of course, then you get a lower number of differential equations. Now, usually, to approximate or to compute a PDE, you use specific techniques, such as finite difference for 1D, finite areas for 2D, or in general, finite element methods for 3D PDE equations. And they are discretized, and the resulting system of the ordinary differential equations is of this form. These are sets of second-order differential equations, such as usually they look like, these are like mechanical systems. You recognize mass, damper, spring, okay? And typically, again, these matrices are huge, of dimension 10 to the power 5, but these are second-order differential equations. So if you want to have first-order differential equations, then you multiply this with 2. It gets twice the number. Okay. So how to do real-time simulations for such numbers, of equations? Furthermore, they are parameterized. So how to do this? You need approximation. You need model reduction for this. Okay. Then we were talking about power systems. Okay. Oh yeah, no, this is something else. This is a so-called SMB, simulated moving bed. This is used in chemical industry. And you can see the scheme for such thing in these pictures here. Okay. So again, we are dealing with some flows and stuff which is governed by differential equations or fluid dynamics, and this results also in PDE models. So this is complicated once again, okay? And here we show you the mathematical model of an SMB process. This is a section of a column, of the process, okay? And you have a number of columns which is given by n-col, and each of them is governed by this set of nasty partial differential equations with initial and boundary conditions. Okay, you know that PDEs must have initial and boundary conditions, right? This is very difficult. Okay. So this is what do people actually do to model such a system? So how do you mathematically model an SMB process governed by the pictures and the equations I have just shown you? So you've got a PDE systems with a couple of n-col columns. You do spatial discretization of the PDE, and you come up with a differential algebraic equation system. This is what DAE stands for. Yeah, DAE is differential algebraic equations. Okay, this is what DAE stands for. ODE, ordinary differential equations, DAE, differential algebraic equations. So once you do this spatial discretization, you end up with a complex system of nonlinear and parametric differential algebraic equations. Okay, this is a nonlinear term here, as you can see. Okay, again, dimensions are blowing up. Okay, dimensions are blowing up. So again, this is very difficult to use and to manipulate in this form. So the question is, how do you want to find the solution of such large ODEs and DAEs? Do you remember what the solution of this equation is? What is the solution of this equation? How you compute the solution of of a differential equation or differential system? Do you remember first order? Are you people familiar with this? Hmm? Are you familiar with solving a differential equation first order? Hmm? I guess not. So let's go back to the scalar case, because this is scalar case means let's shrink n to 1. So you have this differential equation, ax plus bu. A is a real number. Usually this the solution, the Cauchy problem tells us the solution of this differential equation x, the general solution of such an equation, the total solution of such an equation is the general solution of the equation plus the particular solution of the equation. The general solution of the equation xg of t is the solution of the homogeneous equation x dot is ax. This is called the homogeneous equation associated to the differential equation. Okay? How do you solve this? To solve this equation, we are going to use the method of variable separation. So you separate the two variables in two different terms. So everything with x is going to the left. Everything with x is going to the left, and everything in t, the time, stays to the right. So you write the equation like this: x dot over x equals a. Then you rewrite this d to dt. Since you move everything in t to the right, you perform this abusive writing of this type: dx over x is a. Okay, is a dt. You do this, okay? It's a dt. Yeah, because so this is what? Dx over x dt. You can write this. So you do the separation of variable. I told you everything depending on time to the right, everything depending on x to the left. And then the theory tells us that we can integrate. So we integrate to the left from x0 to x dx over x. And here you get integral from 0 to t from a dt. Okay? So then, this is, what is the integral of 1 over x? What is the integral of 1 over x?
Ln dx, ln of x.
Natural logarithm of x, ln x. Exactly. So this is ln x from x0 to x. Okay? Don't mind x appearing twice. This is abusive, but you understand what I'm talking about. Here I should have used another letter, but it's useless because we are engineers. We know what to do here. And this is AT. So this is ln x is AT plus ln x0, which means that x is e to the power AT plus ln x0, which is e to the power AT times e to the power ln x0. So this is x0 e to the power AT. So this is the general solution. This is xg. This is xg. Okay, so we have this part of the solution. We now need this part. This part, the theory tells us, and I'm not going to get into detail, it's the same like the general solution, but changed. So this is integral from 0 to t, from e to the power a, e to the power a, t minus tau, b, not capital, but small b, b, u of tau, d tau. This is the particular solution. This is the particular solution of such an equation. Okay. Now, this here, okay, can be extend to n, to larger n, and you get xg of t is the initial condition x naught exponential of the matrix A to the power t. This is matrix exponential, where e to the power at is identity plus at plus a squared t squared plus and so on and so forth. Yes, this is a Taylor series, not serial. Taylor series expansion. It's a Taylor series expansion of e to the power at around 0. This is how you define the matrix exponential. Okay. That being said, we go back to the general system. Okay, we go back to the general system. So how do you find the solution of such large ODEs, DAEs? Okay, we have, so the solution of the equation x dot is ax plus bu with the initial condition x of 0 is x naught and A an n-dimensional square matrix. Okay, so we, like it's mentioned here, we're going to have a full recap of all these things, so you need not worry that you don't understand a word I'm saying. You're going to get a fresh recap and recollection of all of these notions, and for those of you who have not attended our undergraduate studies, this is going to be new, but it's a lecture in systems engineering. Okay. So the solution of such an ordinary differential equation is of this form: x of t is x free or x general of t plus x forced of t, because this one depends on u. This is the free term, the solution of x dot is ax, and this is the solution with respect to the exogenous influence, the influence of the input u over this equation. Okay. So it's impossible to plot this waveform of x of t by hand. Okay, because so you need computers to compute the x of t numerically and plot x of t at many samples of time, just like MATLAB is doing. Okay, so we need to use MATLAB on this thing. So it's difficult to compute xt following analytical formulations if A is very, very large. Okay, so we need to solve this linear time invariant system. This is a linear, this equation OD gives us a linear time invariant system numerically using numerical methods. So if the system is very large and the computational effort is too high and the results are not so good, or we are unable to extract any results from this, the solution is given by model order reduction. Okay. So our intuition tells us that a linear system is complex if the dimension of the matrix A is very, very large. Okay. And I just told you, I already answered this question. Is this idea true for the nonlinear systems case? And the answer is no. We are going to have a short break now. I'm suggesting a short break. Do you guys agree?
Sure.
A short break. And when I come back from the break, we are going to see a couple of nonlinear models and see how small equations can be quite complex. Okay? All right. I'll be back in 5. Okay. So back I am. Where are you still here?
Yes, I am here.
Yes.
Yes.
Okay, thanks. Okay, let's look into some other nice mathematical models that can cause issues once they get interconnected and form a bigger system, such as the neuron, for instance. Neuron, which is a biological system, an anatomical system. It's the neuron is one-celled with axons, dendrites, transmitting information in and out. Okay, and then the connections are the synapses. Yeah, they are the neural connections. We all know that, or at least that's how anatomy tells the story. Okay. How can this be modeled by a physical or a mathematical system? The neurons communicate with each other through electricity. Okay, so through a so-called action potential, which gives the nervous flux. Okay, so essentially they say here the neurons communicate through an exchange of positive natrium and potassium ions. Okay, there is a balance between these guys that makes the neural transmissions, so which are quite accurate, as we know. So a change in the ion concentration inside or outside the neuron is generating some sort of voltage spikes, which are electrical impulses, okay, transmitted through the synapses. Okay, this is how the information is exchanged between the neurons. Okay, and these dendrites, these interconnectors, they catch this signal, okay, and they transmit it further, and so on and so forth, through the entire biological neural network that we all possess. Okay, so the neural activity, the so-called state of the neuron, depends on the membrane potential. Potentials which is influenced by some other potentials which are called postsynaptic, which are of two types: excitatory or inhibitory. Okay, so we've got in this case two mechanisms identified. There is an activation mechanism and a signaling mechanism. Okay, so based on all this information, an electrical model can be constructed, can be built to describe the functioning and the functionality of a neuron. Okay, the mathematical model is of the type of the mathematical model that we can use for such a neuron is the RC circuit. Okay, so a resistor capacitor circuit, which is governed by this apparently simple differential equation. Okay, this apparently simple differential equation, which is a nonlinear model. So we have here the EJ is the potential equilibrium of ion J. The GJ is the conductance of the channel J. The IJ is the current on channel J. Then we have the injected. In is the injected current in the cell. V is the membrane electric potential, and C is the capacity of the membrane. And you get this model shown in this diagram. Okay. Now, let's see how we can put together the equations of the functioning of a neuron. So the neuron is essentially, from a mathematical point of view, a nonlinear model, which is basic for the process of learning. Okay, so essentially all these notions for neural networks, artificial neural networks, learning and artificial intelligence are based essentially or stem from this physical, biological, mathematical model, which is governed by two equations of this type,
Sorry, I think we're not seeing the shared screen anymore. I'm not sure. Maybe
Yeah.
it's just me or.
I'm
I can
seeing,
see it.
Okay, okay, so it's my fault.
yeah, okay. But you don't need to mind anyway, because you can easily open all these things in OneNote, the Microsoft application, and there you can see live whatever you like. Yeah. This is so we are communicating now through the so-called OneNote notebook, which is assigned to this class. This is the notebook of the class, and this remains throughout the entire course in the system. And you can always download it and you can always consult it. Okay, I forgot to mention that. The OneNote notebook of the class. So you've got here a two-state nonlinear model with two states V and R. These are the variables of the differential equations, the unknowns which need to be computed, with the two quantities M infinity and R infinity fixed. Okay. Now, manipulating this model, you can get a so-called general model to emphasize the two processes, the activation and the signaling. And you've got two equations here. Two nonlinear equations of this type, where gx is usually a so-called sigmoid function. It's called sigmoid because the graph of this function, so this is a sigmoid because the graph of this function looks like an S. This exponential is a sigmoid function. So essentially, this is if this is the model of one neuron, okay, with consisting of two equations, so it's a two-dimensional sort of model, one differential equation and one algebraic equation, one for activation and the other one for signaling. The neural network, okay, is made of n neurons of this type. So I goes from 1 to n. N can be quite a large number if you're dealing with a large neural network. Okay, so this is a large scale complex number, but if you can see here, even if n is small, due to the equations that govern each neuron, even if n is small, you still get a complex model. And it's quite complex because it's nonlinear, because it contains these interesting sigmoid functions in it. So this is another example of a model that can have a limited dimension, but can still be complex. Okay, because it's difficult to compute. A more practical example of all these things we have seen until now is the so-called, this is a model from electrical engineering. Okay, so this more practical example is the so-called DC to DC Chuk converter. Chuk is the name of the guy who invented it. Okay, this is a DC to DC converter. We have here a switch between U and U1, as we can see here. This is an average model of 4 states, nonlinear, not large scale, but can be quite complex. And here you have the 4 equations that govern this model. This model is also present in one of the papers you have to study for the exam. And there, nonlinear model reduction is performed, and some interesting results have emerged. So here we explain what the variables are, the states are, so the currents, the voltages, and these quantities, L1, C2, and so on, they are positive parameters. E is a real number, and the U of t is a control signal, which is between 0 and 1, and it has some physical meaning, is the so-called slew rate of a PWM circuit to control the switch position of the converter. So it contains another circuit controlling or yielding this continuous control input between between 0 and 1. Now, we can approximate this Chuk converter. We can have some methods, and you will be able to see them in the paper to study. For instance, this fourth order, this is the Chuk converter, as you've noticed, is a fourth order model. However, manipulating this fourth order model with specific model reduction techniques, we can approximate it with a scalar system. So first order model, it's a first order model consisting of only one equation, which is this one, and this is the output equation here. Okay, a very simple equation. And the question is, how did it become so simple? Is this model a good model? How can we measure the accuracy of this model? Does it behave like the original? So these are very natural questions, because the two objects are not the same thing. One is the original guy, the second one is an approximation of this guy, and we have to ask ourselves how good this approximation is. What has been lost in this process? What did we lose? Okay. The answer to all this question is given by model reduction, by this field, which we study in this lecture, model reduction. Because model reduction is doing it systematically, and I wrote here in a control simulation learning fashion. Okay, so it follows certain principles and it follows certain goals. Essentially, I'm using the control goal in this for this purpose. Okay, so we'll see how this is performed, how model reduction is performed, I'm saying here baby steps to understand model order reduction techniques for linear time invariant systems. So first we are going to understand what linear time invariant systems are, what their properties are, and how they behave, and what controlling these things means. And later on, based on the notions defined here, we are going to present a couple of methods to perform model order reduction and approximation for these systems. We are going to present them in a nutshell, and you, since this is a research master's program, you are going to perform quite a lot of research and look in the books to deeply understand these concepts in model reduction. Okay? Right. So now if we perform some simulations for this DC to DC converter and its approximation for specific inputs, such as the two signals U that we present here, we can see the red graph, the red picture is the original model, and the blue picture is the approximation. The blue picture is the approximation. What do we see? We see that in the transient, okay, both the models are quite different. Essentially, they don't mean nothing to each other. However, the nice thing is that the first order model is able to capture the steady state behavior after a long time. Is able to capture the steady state behavior. Steady state means no dynamics, the equilibrium behavior of the system. In both cases, here at 0 and here at some value above 0, at some small value above 0. So what have we noticed? The approximation is good in the steady state. So probably one might wonder, is this a criterion to do model reduction? The answer is yes. So the idea is that once you get a model that you need to study and you need to approximate, you look at the steady state of that model, because essentially the main criterion you can impose is to have a similar steady state behavior, the original and the approximation. For the rest, of course, there is other criteria you can impose for the models to have a resemblance to each other. Another interesting model that we have here is the model of a synchronous machine connected to an infinite bus. Okay, this is a power systems model, This is a power systems model. So this synchronous machine is generating power. It's going through a transmission line towards the rest of the world, okay, to the grid, essentially, to the power grid to which it is interconnected. Okay, so this is one machine in the whole power grid, and we are trying to model this machine interconnected to the entire power grid. Essentially, this is an electromechanical system. This is an electromechanical system. It's a machine that generates power. Okay, it's an electric motor that is generating power. The model has 8 states, 6 current and 1 angle and 1 angular velocity. So 6 currents are the electrical, represent the electrical dynamics or the electrical part of the system, and the angular velocity and the motion equation represents the mechanical part of the system. Okay, it's a high-dimensional system to have 8 states. So for nonlinear stuff, 8 is quite a lot. And it is endowed with important physical properties. For instance, this system is passive. I'm sure, since you're all, I hope you're all engineers here, you people understand what a passive device is. What is a passive device? What do you know of a passive device? What do you think it is? Can you tell me, please? What is a passive device, please? And can you give me an example of a passive device?
A battery could be a passive device.
A battery, yes, yes, but an even easier one. An easier example of a passive device. Can you tell me, please?
A resistor.
A resistor, exactly. Very good, very good, very good. So the passive device is the device whose internal energy is not increasing. The main idea is that it's not going to blow up. Yeah, it's the internal energy. Even if you provide external energy to it, the internal energy is always decreasing to a constant or zero level. Like the electrical bulb or the resistor. The simplest example of a resistor is the electrical bulb in lighting. Okay? So the bulb, what happens? It's heating up. The heat generated by the bulb is the passive part, is the lossy, actually, is the lossy part because it's losing energy, internal energy. Okay? Otherwise, it blows up immediately. Okay? This loss of internal energy essentially is an issue, or helps us induce the idea of stability of a certain device or a certain system. Okay, so it's an important property. It's interesting. The question is, the thing is that even if this model is simple or complicated, usually such generators are interconnecting such generators form the power grid, form a power grid. And this power grid can have millions of equations. Okay, so let's go back to this model and say that an 8th order model, which is complex and difficult, can be approximated physically with a 3rd order model, which is usually used in industry, and a 2nd order model, essentially a pendulum-like model for control. Okay, So how is this happening? How is this going? So this is essentially the model of the synchronous machine, consisting of one field winding, 3 stator winding, a circuit, an amortizer circuit on the d-axis, an amortizer circuit on the quadrature axis, and all of them are magnetically coupled. All of these are information from electrical engineering. Okay, this is a 3-phased machine essentially. It has 3 phases. However, someone was smart enough to be able to say that 2 axes are enough, the so-called DQ framework. Okay, so you get rid of a phase, and thus the model is simplified. The electrical model is simplified. Okay, then the symmetry of the rotor and the magnetic circuits with respect to these DQ axes, okay, show us the synchronous characteristics of this machine. We do not get too much into the details of the physics of this machine, but we are interested in the equations. Okay, this is how the model, the schema of the model is presented. Okay, this is how they look like, and the circuit, the rotor circuit and the stator circuit. It's shown here. Okay, and these are the variables that come into the modeling. Okay, so we do have electrical equations. We have stator voltage equations, a couple of them. We have rotor field voltage equation. Okay, so we have here fluxes, yeah, and we have rotor voltage equations. Okay, and of course we have other 2 parts. We have the mechanical part of the model. Okay, we have the mechanical part of the model, which is the swing, which is the motion equation. This is the most important part. This is the one generating mechanical power turned into electrical power. Okay, and we see here a rotation equation. Yes, J is the inertia of the rotor, is the inertia of the rotor. Omega is the angular velocity. Omega dot is the angular acceleration, and this is the equation that is governing the motion of the rotor. Okay. Furthermore, like I said, this machine is connected to the rest of the world. Is connected to the bar grid. So we have network equations which are a couple of algebraic constraints. And we can manipulate these equations. We can manipulate this equation to get finally the eighth order model, which is this guy. Here you've got 3 equations for this guy. This is how the model looks like. It may look simple, but it's not, because you have here coupled variables through polynomial products, as you can see here. So they're not easy at all. They are not easy at all. Okay. Of course, you can write. You have relations between fluxes and currents. Fluxes are inductances, is the inductance times currents. And if you build up 2 vectors, one with the fluxes, the other one with the currents, you can easily build up the so-called inductance and self-inductance matrix L. Okay. And so this is the full model. Again, this is the full model of the single machine connected to the infinite bus. And it shows, next we show that how the energy discussion, how the energy assessment of such a system is performed. So this machine has a total energy. As you can see here, you have all these quadratic terms. This is a matrix quadratic term. Okay. And it can be written in this fashion. It can be written like here. So this is indeed a quadratic energy. Yeah, this is a quadratic function. Energy is a positive function. Okay. So this is indeed energy. this is indeed energy. P here is J omega, so this is the momentum of the rotor. The idea is that if you choose power conjugated outputs, meaning the input and the output product, the product of the input and the output is power. That's why they are called power conjugated outputs. So if your inputs are voltages, your outputs are currents, and vice versa, the system can be proven to be passive. Mathematically can be proven to be passive in the sense that this H is never increasing when the ports of such a system are supplied with electrical energy. Okay, and this leads, okay, to stability. Essentially, this leads to stability, so the system can be stable. Now we've had all this discussion about this equation, and we are noticing that this is a complex model, difficult to use, especially if you get this to be large scale and to use on large scale interconnections. Okay, so we can present simplified lower order models which can be used in industry and control. Okay, in industry and control. Yeah. Okay. I'm suggesting here that for the lecture we can stop here. Okay. The question is, you said you people are familiar with MATLAB, right? You're familiar with MATLAB. I'm suggesting that you do you have access to MATLAB? This is something I haven't asked you.
Yes.
You have access to MATLAB. Fine. If you have access to MATLAB, then open the MATLAB and try to open the 3 models from Moodle. Yeah. So I'm going back. I'm going to show you the Moodle once again. Okay. So go to this folder called Simulation Models. Download the files. Open MATLAB and generate the data about each of these files, about the building, about the pendulum, about the CD player. Okay? Once
Can you repeat, please, what to generate?
The data. Okay, so load these files. There is a MATLAB function called load. Okay, that is loading into the workspace the matrices and the data of these files.
Okay.
Okay, let's have it loaded and then later meet again and do some simulations. Look at the dimensions of these models. Okay, because then we'll start to explain what these models essentially mean. Okay, let's just have a look at them first. That's all. That's the only thing I want to do today in MATLAB with you. Okay, look at these things. Yeah. All right. I'm opening my MATLAB as well. I'm also going to download the files. Right. So simulation models. I don't think that Moodle is difficult. I think you can easily use it. Have you been able to download them?
Yes, I also loaded them in MATLAB.
Oh, you have already loaded them. Okay, let me also finish this process. It's good that you have access to MATLAB because I cannot provide MATLAB for you. I can't give you licenses or nothing for that matter. Okay. You have to manage yourselves. I think you can also use Octave.
Or maybe Julia.
Who's Julia?
Julia is a similar language to
Is
MATLAB.
it? Oh, I didn't know that. I knew about Octave, which is online. Okay, fine, whatever. I don't mind as long as you have some MATLAB access to some MATLAB. I'm fine. Okay. Okay. I'm trying to share my screen once again with my MATLAB. There you go. So load, but I think I have to Let's see, load. Player.mat. Okay, now the thing is that I have to give the path, right? So I'm going to open this. Simulations. And this is something else. I just needed to run this to be able to. Because I didn't know how to put in the path. This is the only trick I could use. All right. It's doing something. So I'm going to clear the workspace. So I loaded the mat. As you can see in the workspace, you've got the matrices A, B, C. They represent the matrices of the differential equations, okay? They represent the matrices of the differential equations. And other data about Hankel singular values, we'll see what those mean about this mat thing. So the model is given by the three equations. Yeah, you have x dot is ax plus bu, y is cx, and the matrices A, B, C are yielded by the CD player mat. Now we need to make these matrices because these are structures. So we are going to use full to turn this into matrices, full A. We are going to put comma because we don't want it to show. So now it's a double. So if you put A like this is the matrix A, okay? But we are not interested in this to see the whole matrix. So we're going to check the size A, to see how many equations. So the CD player, look, the size is 120. Please confirm that you're seeing my MATLAB screen.
Yes, we can see it.
Yes.
Okay, thanks. That's great. So the CD player model is governed by 120 equations. This is quite a lot. This is quite a lot. Yeah, 120 equations. CD player is a classic benchmark model for model reduction, by the way. This is not something I'm cooking up. It has been used quite a lot. And we are going to check an important website, which I discovered recently. So this is difficult. For instance, if you want to use this A to compute, I don't know, you need to compute something. For instance, the eigenvalues of A. Yeah, you want to see the eigenvalues of the system, the modes of the system. You perform the command EIG from eigen means own. By the way, eigen or eigen in Dutch, and eigen German means own, its own value, yeah, eigenvalue. So eig of A is the set of eigenvalues of the matrix A, as you can see here. Yeah. So these are 120 eigenvalues. These are difficult to compute. Okay, 120 MATLAB can still manage. MATLAB can still manage 120, but maybe not always. Maybe not always. Yeah. 120 is a little. You can generate. You can generate. You can use the command rand. Okay. You can use the command rand and generate random matrices of random numbers. You can generate matrices of random numbers, and here using rand you can easily so rand n is an n by n matrix with pseudo random values drawn from the standard uniform distribution. So okay, so rand 10, this is a 10 by 10 matrix. Okay, so aig I of ans is easy to compute. It's easy to compute. You can see here the eigenvalues of this matrix. Okay, but then you can check, you can use by yourselves, and I invite you to do that. And this is what I'm giving you. It's not an assignment. It's some sort of homework for you to use this rand to generate huge matrices. Okay, and then check if MATLAB can still do the eigenvalues. And you can tell me next time which dimension stopped being accurate and properly computed by MATLAB. Okay, so the CD player is 120. It's got 120 eigenvalues. Okay, what you can do is compute a system, a state space system for A, B, C, and zeros of 2 by 2. I think it's got 2 inputs and 2 outputs. Okay, so this is the dynamical system. This is the dynamical system, which I have forgotten to give a name to. This is the, look how big is the dynamical system computed using these matrices A, B, C. MATLAB knows how to turn these matrices, it's impossible to read, how to turn these matrices into so I should give a name to this. Let's call it CD. Okay. Now I'm going to put a semicolon, so it's not going to show it anymore on the screen. We've got a state space system. Now we are trying to simulate it. We're trying to simulate it. For instance, let's check the step response. The heavy side. Do you know what the step signal is? Are you people familiar with this signals? A step signal. No? A step signal. Heavy side step signal. The step signal is a constant signal of value 1, is the harmonic system of frequency 0. That's what it is. It's the easiest way to explain to people who don't know, who do not understand signals, what the step signal is. Is the sinusoid of frequency 0. Okay? So it's sine of 0t, it's 1 for time, for positive time, and it's 0 for negative time. Okay? So if I put an input, if I'm giving to this system an input of a step, how does the output look like? And this is the command step in MATLAB. This is the command step in MATLAB. Look, it's difficult to compute. It says busy here, and it's trying to build a picture. It's trying to build a picture using all this data. Takes a while. well, now it takes a while for the graphic board to show us an image, but that's another story. We're waiting for the results. It's plotting now the results. So for a limited machine like mine is, it shows you that for a limited machine, and of course all machines are limited in some sense, the computation can be quite cumbersome. Even the numerical computation with all the numerical tricks involved, okay? It can become quite difficult. Do you agree? Okay, now it should show something, but it's not. Oh yeah, here it is. Yeah? Are you seeing this picture of the step signal or not?
No, we are not.
Not yet.
Because I'm sharing only one. Let me reformulate the share screen. Okay, so I'm going to share the entire screen. Okay, so you can see everything that's going on my screen. Can you see my screen again?
Not yet.
Not yet, but you'll soon be able to. How about now?
Yes, we can see something.
Okay. Can you see this plot?
Yes.
Okay, so look at this plot. This is the step signal of all the outputs of each output with respect to each input. So from input 1 to output 1, from input 2 to output 1, from input 1 to output 2, from input 2 to output 2. Okay, look at this oscillations here. Can you see these oscillations? Okay, so if you approximate such a system, you need to capture back some of these oscillations. But as you note, if you noticed on this on this slower computer like this one I'm showing you on is, it takes a lot of time because there is a lot of equations involved. Okay. Let's also check what else. Impulse response. Impulse is the Dirac, is an impulse that you give to the system. Impulse of CD. Okay. Let's check the plots. This is the impulse plot. It's stable indeed. As you can see here, this is the stability because they all go to 0 in the end if you give them an impulse. So as you can see on this limited machine, that's what I'm trying to show you. Having a complicated system takes a lot of time to perform simulations. So imagine if you do control design, how difficult it is to perform control. You agree with that, don't you? Right? So the larger the system is, the more difficult the computation is. That's what I'm trying to show you here. Let's check the other models as well. So I'm cleaning the main screen, and I'm also going to clear the workspace. And now I'm trying to load building. Let's look at the building. Building.mat. Unable. Building. BUI. Building. It's loaded. As you can see here, it's a 48. If you look at the size, it's a 48 type of matrix. Okay, so building is now a system, and I'm using the same command SS, state space, of A, B, C, and D. You have 4 matrices. D is 0 in this case. We don't mind. So this is the model building. Let's check again the eigenvalues of the matrix A, because these are important to check whether the system is stable or not. Checking stability, is not an easy task. Checking stability, because stability, as you will see in the next lectures, is completely or bijectively related to the eigenvalues of the matrix A. Computing these eigenvalues is not an easy task. So if the dimension is very large, and you can check this yourselves, asking MATLAB to perform huge dimensions, computing these eigenvalues is a very difficult job. Even if you want to use, for instance, a Lyapunov equation, a Lyapunov matrix equation to assess stability, is still very, very complicated. It's very complicated. This is a 48th dimension model. Again, we check the response to the step of the building and see how it behaves, because this is important. So we have 1 input and 1 output. Okay. So if you give this building a step nudge, in the end, it will go to 0. Okay. It's a nice simulation, as you can see here. Okay. We are going to check the impulse. So if we set an impulse for this building, impulse, of the building. Let's see how it looks like. Let's check the picture. This is how it looks if you give an impulse to the building. Okay. Again, the building is a 50th order model. I would like to approximate it with a second order or a third order model, so I can do a lot of stuff with it. Also, keep in mind that in control we have an issue. People who have already studied control engineering in the undergraduate studies already know that the dimension of a controller is usually equal to or larger than the dimension of the system. So if you compute the closed loop system, you get 2n, at least 2n dimension, and that's even more difficult. So dimension is an issue, okay? And now, finally, let's clear everything. And let's go to the last model, the cart controlled by a double pendulum. The cart, this is a 6th order model, so this is very easy. The results are instantaneous. You can see that all the eigenvalues are in the open left half plane. So the system is nice. If you perform step, I did not build the system. C2P is SS. We are going to recall all these commands A, B, C, and 0, because there's 1 input, 1 output. This is how the model looks like. And now you do step C2P, not 3, but 2P. And the result has been almost instantaneous. The picture has been almost instantaneous, and you can see this one. It stabilizes, okay? And also, if you plug in impulse, C2P, you can check. This is how it looks like. so it stabilizes as well. So the graph is nice. Okay, so what I want you to do at home is okay, you cannot generate A, B, C because that's maybe a little difficult, although it can be done. You can try to generate your A, B, C, look A, B, C, but at least generate the matrix A, make it a large matrix, so generate using random numbers, take a dimension of thousands or tens of thousands, and try to compute the eigenvalues or try to solve a simple linear algebraic system, AX equal to B, and see what problems you run into. Okay, check what problems you run into. Have you got any questions, please, for today? I'm taking questions now. I haven't got anything else to say for today. Questions, please. Hmm? How do you find the subject?
Personally, I find it quite interesting, and I'm sure we will have to apply dimensionality reduction.
Model
very
reduction.
interesting and
I'm
very
not sure.
useful nowadays.
Can you repeat, please? I haven't quite heard you. Please say again.
Excuse me. I said very interesting and very useful nowadays and in the near future.
Yes, not in this country, I'm afraid. I'm sorry to say that. However, if you run into needing to do optimization, so if you need to do optimization, these things can be very interesting. Also, if you work in some a company that needs automation, okay, and you're dealing with complicated models, this is also a solution for those things. I'm afraid, I'm going to be very honest with you, I'm afraid this is more of a research subject at this time. If it gets useful for you in the future, I'm very happy about it, but I cannot predict this at this moment. At this moment, I'm happy if you people can understand a little bit the subject and the procedures. And I honestly, if you're really interested in the subject, I honestly invite you to read those books. Those books you have in Moodle, I think they can be very useful and give you a very nice view of how things can be done also in industry. Okay? Okay, so I do thank you for your attending today. I invite you to play with those matrices and those very large matrices, and I'd like you to tell me next time how your MATLAB got stuck and blocked. Because if you take a 100,000 random matrix, I'm sure MATLAB is going to fail on your computer to be able to compute its eigenvalues. And if you have nothing else to tell me, I'll see you next time.
Okay, good evening, teacher.
One more thing. Please know that since our classes essentially are supposed to end at 8 o'clock, I'm going to leave this channel open, and if you have any questions anytime, any Thursdays until 8 o'clock, you can still call me and find me here, okay?
Okay.
I'm available for you. Okay? So you
Okay,
people
thank you
can
very much.
you people can leave, and I leave the call open, and you can join again if you have questions or you need to tell me something. Okay.
Okay. Thank you. Have a nice evening.
Have a nice weekend. I'll see you next week.
Thank you. Have a nice weekend.
Cheers. Cine să fie studenții? Erau 4 băieți. Din 8. Sunt 8 cu totul. 8 sau 10. Prima oară, după ce ceva vrem să venim după 6, că știți, mai avem de lucru. Și chiar venim de la 4. Ți-am povestit că s-a apucat unul să scris un articol foarte supărat de decan. Exact, și pe aia, și pe aia. E studentul meu. Anul 4. Vlad, nu știu cum, Oancea, nu Oancea, nu știu cum. Orcescu, parcă. Nu să știu. Că nu de mine, dar nu cu ăștia. Și am ultim acolo. Dar scriau unii că, Doamne, asta e un zăvăcist, ceartă cu toți, să înjură cu toți profesorii, întâlbit, ziceau unii. Alții, vai de mine, ești mare revoluționar. Știi? Știi cum e la noi cu Revoluția, tovarășilor? Dar noi că prin Revoluție. I-am scris 2 ore, zicând o să vedeți că voi student am ăsta care a scris articolul. Nu, că nu mi-a răspuns. Am să văd de el. Să se certe ei acolo. Eu mi-am văzut de treabă. Oleu, să închid și camera. Camera nu mai trebuie.